In this project, we'll build a night lamp that reacts to its environment. An LDR senses the light level. The ESP32 decides whether it's dark, and PWM lets us control LED brightness smoothly and automatically. So far, you've learned the basic robot pattern: sense, think, and act. You met the ESP32, then used it to control LEDs and a buzzer with timed outputs. Now we'll add an LDR sensor, so the project can respond to real light conditions instead of only following fixed timing. The goal is to build a lamp that reacts to its environment rather than using a manual switch. The LDR senses how much light is in the room and sends that information to the ESP32. The ESP32 compares the reading with a threshold, then decides: if it's dark, turn the lamp on. If it's bright, keep it off. This is the same input-process-output pattern used in robotics. A sensor provides information, a controller makes a decision, and an output device performs the action. Before we build, make sure each part has a clear job. The ESP32 is the controller. The LDR senses brightness. The LED and resistor create a safe lamp output. The breadboard, jumper wires, USB cable, and computer let us connect, power, and program the system. An LDR is a light-controlled resistor. When more light hits it, electricity can pass more easily, so its resistance goes down. In darkness, the path becomes harder, and resistance goes up. To read that change with the ESP32, we use a simple circuit that turns changing resistance into changing voltage. That voltage becomes an analog signal the ESP32 can interpret as brightness. To create that signal, the LDR and a 10K resistor share the 3.3 volt supply, forming a voltage divider. As the light level changes, the LDR's resistance changes, and the voltage at the junction changes too. That junction connects to an analog input, such as GPIO34. The ADC converts the voltage into a number, like 512, which the program can use to decide whether the environment is bright or dark. An LDR is different from a button. Instead of giving a simple 1 or 0, it changes gradually as the light changes. The ESP32's ADC measures the resulting voltage and converts it into a number. That number may rise in brighter light or fall, depending on how your voltage divider is wired. The key habit is to watch the serial monitor while you change the light. Shine a lamp, cover the LDR with your hand, then uncover it. If the readings move smoothly, your analog input is working. Light sensor numbers only become useful when you connect them to real conditions. A reading of 320 might mean a bright classroom, while 45 might mean a dim corner. But those numbers can change with the room, windows, and sensor position. Before choosing a darkness threshold, test several situations and write down what you observe. That is an engineering habit. Measure first, then decide what the lamp should do. A threshold gives the ESP32 a simple rule for making decisions. Instead of trying to understand day or night, the program compares the sensor reading to one chosen value. In the bright range, it keeps the lamp off. When the reading crosses into the dark range, it turns the lamp on. This is how raw analog data becomes action. The same pattern appears in alarms, thermostats, and automatic systems. Measure something, compare it to a threshold, then choose a response. Now we turn the sensing idea into code. First, analog read reads the LDR voltage and stores it as a number. Then an if statement compares that number with the threshold you choose. If the reading means the room is dark, the program uses digital write to switch the LED on. Otherwise, the else part switches it off. Printing the LDR value and lamp state to the serial monitor helps you confirm that the threshold is reasonable and the rule is working correctly. PWM is how the ESP32 creates brightness levels, even though the output pin is still switching between on and off. It turns the LED on and off many times per second, faster than our eyes can follow. What matters is the duty cycle, the fraction of each cycle spent on. At 20%, the LED receives power only briefly, so it appears dim. At 80 or 90%, it is on most of the time, so it appears bright. By changing the duty cycle gradually, the lamp can fade smoothly instead of jumping between off and on. With PWM, we can move beyond a simple on-off threshold. The LDR gives us a changing number, and we translate that number into a PWM value from 0 to 255. When the room is bright, the PWM value stays low, so the LED is dim or off. As the room gets darker, the mapped PWM value increases and the LED brightens smoothly. This is called mapping, converting one input range into a useful output range. It makes the lamp feel more responsive and intelligent. Real sensors are not perfectly steady. Even when the room lighting looks unchanged, the reading can bounce a little. If your program uses one exact threshold, those small jumps can make the lamp flicker on and off. Smoothing reduces this by averaging several recent readings, so one noisy spike has less influence. Hysteresis solves the problem another way. It uses two thresholds. One threshold turns the lamp on, and a separate threshold turns it off. That gap gives the system room to ignore wobble near the decision point. Now bring the project together carefully. Wire the LDR as a voltage divider, confirm 3.3 volts and ground, then connect the analog input and the LED with its resistor. Upload your code and open the serial monitor before judging the lamp. Watch the numbers in normal classroom light with a flashlight and when you cover the LDR. If the LED behaves backwards or does nothing, slow down. Check each wire, resistor value, pin number, and threshold. Most problems are simple mismatches between the circuit and the code. You've now built a complete sensor-based system with the ESP32. The LDR turned brightness into analog values, your threshold logic decided when darkness mattered, and PWM made the lamp fade smoothly instead of only switching on or off. Next, you'll apply the same pattern to a mini weather station, measuring temperature, humidity, and more. Your ESP32 is becoming aware of its world.